Ready to go? All right, Dr. Macko joined the Physics and Engineering Department at ENC in the fall of 2014. She has just finished with her PhD at MIT, where her doctoral dissertation included fabrication of ultra-lightweight flexible solar panels and device engineering of sub-100 nanometer thin multi-junction photovoltaics. Dr. Macko has thus far co-authored 4 journal articles and 1 patent application, and she's also introduced her work to the scientific community at several conferences. Her current research aims to explore the fabrication and physics of low capital cost solar technologies from environmentally safe and abundant materials. During her undergraduate and graduate studies, Dr. Macko received extensive training in classroom instruction, in college-level science and engineering pedagogies, skills that she plans to apply here at ENC. Dr. Macko lives with her husband in Arlington, Massachusetts. So it is with great pleasure that we welcome Dr. Macko to the Join You Free Physics and Engineering Seminar Series.
Great, thank you. Thank you all, and thank you for the kind introduction. Yes, so my name is Jill Macko. I teach here at ENC. I see most of you every day, which is great, my pleasure. But very rarely do I get to speak on my actual research, which is fun. So today I will be presenting on my research. All of this today is what I have done so far at MIT, my PhD work. That I've been finishing up a little bit over the last semester and will be continuing here. So in the last slide or so, I'll be discussing my hopes and plans for what I plan to do here at ENC. So today I will be speaking on vapor-processed organic photovoltaics. Specifically, PhD is meant to be in something very focused and very specific, and you become the world's expert on something that's so specific it usually doesn't matter to anyone. But very specifically, I worked on vapor-processed organic photovoltaics with the ultimate goal of efficient solar energy conversion from any surface. I would like to thank, of course, my funding sponsors. They're on the top right, from NSF and ENI, for their generous funding. So to start off with motivation here, a number that still astounds me today is that, if you could see it, more than 1.5 billion people in the world live without any electricity at all. They have no electricity whatsoever. That's 20% of the world's population, which is really an astounding number when you think about how useful electricity is and how we just take it for granted. And how when the power goes out for some thousands of people due to the blizzard, we're all shocked and we feel really bad for them because it gets very cold. So that's how much electricity is important for us. And a little bit of electricity can make a difference. So this is from a project from Panasonic that they just gave out these solar-powered LED lamps. And you can see here the students studying at night. It's shown that their grades and their knowledge will go up if they actually have electricity so that they can study at night. You can work at night, you can have medical procedures at night. So even just a little bit of electricity that will power lighting is enough to make a significant difference in people's lives. The other key thing to know about those people without electricity is that they're actually often in places at the ends of the earth where there's no or little infrastructure. They do not have paved roads. These are people who are off the electric grid. Of course, they don't have paved roads. They are starting, especially in Africa, they're starting to get internet through mobile data. But even to charge their cell phones, they have to go to the nearest medium-sized town that actually has batteries so they can charge their phones. Often they don't even have running water. So that's actually one of the limitations, is how do we get them electricity when there's not even roads there to drive batteries there, or to drive fuel or propane. However, even though they're basically in the middle of nowhere, as we understand it, they do have plenty of access to solar energy. So this is a graph of the solar irradiance that averaged over the year for the whole globe. And in the red parts is where they have the most solar radiation. That's where they're going to get the most power from the sun. And you can notice, actually, it's often matches with those who do not have electricity. We're talking about Africa. They have a large amount of solar sunlight, even though they do not have electricity, also in South Asia. But actually, the truth is solar energy is everywhere. So everyone could take advantage of solar energy. This is from another study that actually areas that are off the grid, so they have no electricity, they have no infrastructure, they have no roads. Actually, it's cheaper for them to buy a solar-powered LED lamp. This is if they buy it at the actual cost. I think this is numbers from 2009 or 2010. So actually, even here, a solar-powered LED lamp is not that cheap. But for them, it's actually still cheaper for them to buy a solar-powered LED lamp than to buy kerosene to power the kerosene lamp, because it's so difficult to get these gallons of kerosene to their houses, to where they live. Plus, it makes a significant difference. You can see here lighting in the left. You probably cannot even tell that the woman is sitting there, or you can see them on the right. So it's brightness, it's health effects as well. It's also the dangers of the burning kerosene is a hazard, potential burn hazard, etc. So it's cheaper for them, and it's better in multiple ways. But however, the question is, do you want just any PV or just any photovoltaic? So photovoltaic is a device that will convert your solar energy into electricity, but there are certain limitations. For example, this is a picture of the most conventional and commonplace solar panels being used by a doctor who's actually transporting medicines across the Sahara. Often medicines cannot be exposed to this kind of heat that you would experience in the Sahara, so they're actually in refrigeration units on top of this camel, and then on top of these fridges on the camel are these solar panels. And you can imagine they're brittle. What I've heard is actually in Africa, for if you try to transport these solar panels, only like 30% of them actually make it to wherever they're going without being broken. That's about 2/3 of them actually break on en route. And so actually the price goes up by 3. Plus, it looks pretty bad for the camel. It looks pretty heavy, right? You wouldn't want to do this. So ideally, you'd want PV technologies or solar technologies that are actually robust and lightweight, such as the example that we have here in the bottom left, something that's flexible for this specific application. Right, but not just camels. Camels are not the only ones that will want lighter solar panels. There are applications around here where people talk about using these solar panels, flexible, lightweight solar panels. For example, if you're camping, in the middle is a picture of someone at the beach, and they're using a solar panel to charge their cell phone. This was actually free solar panels that was passed out by Nivea to advertise their sunblock. You can imagine you'd also want solar panels on your wireless keyboards. People want to use wireless keyboards, but how do you power these wireless keyboards? You put batteries in, and then when the battery runs out, you put a new battery in. But what if you never had to put a battery in your wireless keyboard or wireless mouse ever again? And this guy on the bottom right, he has a little solar panel on the collar of his jacket to like charge his iPhone that's in his pocket. So that'd be kind of cool, right? You put it on your backpacks, things like that. And so there are multiple applications for flexible, lightweight PVs or solar panels, not just of those people who don't even have electricity at all. We in the developed world and also those in the developing world can utilize it. But they're just, we don't have them yet. So just to talk a little bit briefly about PV technologies as they are today, or photovoltaic or solar panel technologies as they are today. In the top left is wafer technologies. That's the most common. That's silicon. If you ever heard of silicon, almost all the solar panels that you'll see nowadays, all of the solar that's coming out of China is wafer-based. That's our silicon. It's very heavy, it's brittle, but it works really well. It's actually so heavy that the majority of the cost of having these solar panels is in the installation, and the installation is very high because of the weight. On the right middle is thin film. So this has become popular over the past couple of decades, especially in the United States. It hasn't really caught on with other countries. The United States is leading the innovation in thin film. It's more flexible, but the efficiency is not as good. But it's not totally flexible, but it's significantly so, and more lightweight. And the bottom left is nanomaterials. So that's my specialty. That's what I focused on. Nano meaning 10 to the minus 9 meters. So it's working with materials that are on the molecular scale, almost the atomic scale, that they have physics that is interesting on those scales. And they can be made very flexible, they can be made transparent. They have a lot of unique and interesting physics that are going on when you're working on the nanoscale rather than on the macro scale. Which, due to the sake of time, I'm not going to go in today, but I spent my PhD on that, so if you're interested in it, I can talk to you for hours and hours and hours about it. But I'm going to try to resist. So I did present almost a year and a half ago now, when I visited nanomaterials. So today I'm going to present on more newer research, but just to refresh your memory, I spent some time talking about our different ways of fabrication. We have the first ever solar panels that are made directly on paper. So this is just showing one of the applications of that. If you have a solar panel that's basically a paper solar panel, you can fold it and it still works. Here we're folding it up, we're crushing it up. Sorry, you can barely see the numbers. How do we have this? This one? Can barely see the numbers here, but this is voltage that has to do with the power that's coming out of our solar panel. Of course, when it's crushed up and it's not getting any light, then the power is basically zero. But when it's spread out, the power goes back to whatever it was before. So we were able to make solar panels on paper, on a variety of other materials as well. Paper is extremely lightweight. We also made, again, this is working with different fabrication technologies. Is this going? No, not. So working with different deposition technologies in collaboration with chemical engineering department, the chemistry department at MIT, we worked on different encapsulations. So here, this is a specific encapsulation that's still flexible, still ultra lightweight. I think this one here in the video is somewhere around 100 nanometers thick, so very thin, and we can actually put water on it and it will repel the water. So you don't have to worry about if it rains, it might like melt something. The paper is not going to dissolve, the paint is not going to dissolve. So we can protect against the weather, different atmosphere. Here we actually submerge it in water to prove that it still works. And we can also increase lifetime. So lifetime is one of the limits of this technology right now, but we've also shown that we can increase lifetime. So this is with different deposition technologies. I'm going to be honest, here at ENC, we can't afford these deposition technologies. But we have friends at MIT. We still have friends there that we can work with here and there. But this basically demonstrates the potential of organic photovoltaics. This is why we're interested in it, because it can be made flexible. It can be made ultra lightweight. And there are other nanotechnologies similarly that can be made like this. But conventional technologies are just not going to cut it. So I've talked a lot about the different potential for OPVs, and I've said here and there PV, OPV, but I haven't really talked about what that is. So first I'm going to discuss a little bit what are OPVs and also why don't we have them yet. So that's the next section of the talk. All right. So OPVs, physical processes. So this is just a cartoon of what's happening in the OPV. So OPV, organic photovoltaic. Organic is similar, is the word that is used in orgo, like orgo chemistry class. Not organic as you'll see at Whole Foods. This is organic as carbon-based. And then photovoltaic is what's going to turn light, so photo lights, which is solar energy, into voltage, like electrical energy here. And so we can say what's happening in a device. We can separate into 3 steps. The first step is you'll get the interaction of a photon and a molecule, your carbon-based molecule, into, they form an exciton. I'm not going to get into an exciton is. It's complicated, and most people actually don't fully understand what it is, sadly. And actually, we're still studying exactly what it is. To tell you the truth, I don't think anyone fully knows. But a photon has to do with light, so you have your light is absorbed by your molecule. It forms this mysterious thing called an exciton. Your exciton can move around, and then it will actually dissociate into charge carriers. That's step 2. So in step 2, it will actually become an electron in a hole. And then in step 3, you can actually collect the charge carriers into your electrical circuit. So you can use it to power your phone, your computer, whatever you want, or your LED light. So these are the 3 steps, but basically we're looking at light comes in, it interacts with the molecule, and then charge carriers come out. Your electron and hole come out. So this is just to simplify things for those of us who are not totally familiar with current and voltage. Current is proportional to the number of charge carriers you're collecting. So that's about the number of electrons that you're getting out of the device that actually is going through your circuit. Whereas voltage has to do with the energy of those charge carriers. So both of these are key. You need to have a number of charge carriers coming. You want to have a high current, but you also need a high voltage. You want those charge carriers to have high energy. And then when you put them together, you get your current, which is number of carriers, your voltage, the energy of the carriers. If you multiply together current and voltage, you get the power. And so your goal is to get as much power out as you put in. So this is your P equals IV. If you've taken Gen Phys, which we actually have not yet gotten into in Gen Phys. But it's okay, most of the Gen Phys students are not here, so surprisingly. So anyways, so P equals IV. Andres, you're going to remember this when we get there. On the graph I have shown in the bottom right, so we have what I call a JV curve. They're also called current density voltage characteristics. That's a fancy word for it, characteristic. But here we're just going to call it JV, where J is the current density. And we're showing in the pink box, that's the power that you get out if you're at 0.1. So power equals the area under the curve. That's the current times the voltage at that specific point. Right. So this is just filling in the actual curve of the photovoltaic. And you get a maximum power rectangle here. So this is your curve of the photovoltaic, then this point gives you your maximum power. And then you can fill in this rectangle, which is basically integrating out what is the area, what is the current times the voltage, and the maximum power that you can get out from this curve. So when you're looking at a solar cell or you're looking at a PV, what you care about is the maximum power that you can get out of the PV. So what you care about is what's the biggest rectangle you can fit inside this curve, inside your JV curve. So that's called PCE, power conversion efficiency. That's conversion from optical power into electrical power, and that's the number that everyone will cite. So if you know anything about a solar panel, probably what you know is the PCE. So that's on the order of 20%. Silicon solar panels are currently around 20%. That's what you buy in the store or buy for your house, things like that. There are also other parameters that you use to characterize solar panels. So the top is what I just pointed out, PCE. That's your maximum power out. There's also your open circuit voltage, which is the voltage at open circuit, voltage where current equals 0. You also have JSC, which is the current where voltage equals 0, so short circuit. And then you have fill factor, which is this very strange, kind of seems made up parameter. Fill factor has to do with the shape of this curve. It has to do with the area of this maximum power rectangle divided by the area of the rectangle if you made a rectangle just with VOC and JSC. But it basically is telling you the shape of the curve. You want the shape to be as square as possible. So that's the goal. So fill factor is actually going to be key in the research that I'll be presenting later in the talk. So that's why I'm spending some time on it. It's basically the shape of the curve. So the more square it is, the more power you're going to get out. Right. So this is a very complicated graph. I showed it to some of my friends. I've been staring at this for the past decade, and so I'm like, duh, it's obvious. And then my friends are like, that's a crazy looking graph. But basically what it is, it's the history of solar technologies. So on the bottom here, in the x-axis, that's the year, so that's history. And then on the y-axis, we have efficiency. That's our power conversion efficiency that I was just talking about. So that's the maximum amount of power that you can get out of a solar panel. And each of these colors and different shapes is a different technology. So silicon's in here, different thin films are in here, different nanotechnologies are in here. What we're going to focus on, the focus of my research or my PhD research is on organic photovoltaics, carbon-based PVs technology, which is in the solid orange dots way at the bottom. So you can start to see now why we do not have these flexible solar panels everywhere, because they do not make much power. We can compare versus the best wafer PV. Wafer is commercial. That's the one that's commonplace where you'll see everywhere. That one's at 29%. That's the world record. 29% is your wafer PV. That means for every 100 milliwatts of light energy that you put into it, you're going to get out 30 milliwatts of electricity. Whereas OPVs are down at 11.1. I've heard reports at 12%, although they're not published yet. So these are the ones that are published. The best so far is 11.1. So that means instead of getting 30 milliwatts out, you're going to get 10 milliwatts out. So it's a factor of 3 difference how much electricity you're going to get out. So it's considerable enough that is not yet commercially viable. There's plenty of other issues. But PCE, the power conversion efficiency, is one of the key ones. Right. So if power conversion efficiency is key, then how can we actually increase it? So for example, in OPVs, the current world record is 11.1. So again, I'm just going to throw out this number. It means power conversion efficiency. We went through the math in my lab. We actually modeled if we had the best VOC possible and the best short circuit current possible, the best fill factor possible. So everyone's research has different strengths. If we said if somehow someone can make a device that took everyone's strength together, then what would be the best practically possible? And we said 17%. So through our modeling, we should be able to achieve 17% if we combine all of the research that everyone has done so far. We should be able to get 17%, so there's definitely room for growth. But the question is, how do we get there? How do we actually achieve this? So there are multiple ways of doing that. One of them is nanostructural engineering. So that's actually looking at different fabrication processes. Through annealing, you can get it to crystallize. You can increase the mobility or the conductivity of different materials. You can work on making these large aggregates, as I'm showing in the right, a beautiful tree by this is actually blue carpane. Blue carpane is a molecule you can get extremely cheap, and so we were working on different deposition technologies to see if we can make it better devices. Unfortunately, I did not spend enough time on that yet, and then there's also solvent annealing in the bottom. So there are different fabrication processes which I explored. Fortunately, none of them worked out over the course of my 6 years of my PhD, but maybe, hopefully, I'll continue this and something will magically work. The interesting thing about PhD is actually this was my interest, and I worked on, this is only 3 of them, I worked on several different aspects of this during my PhD, and none of them quite worked out. But I had another side project, which I wasn't so interested in, but it actually worked out really well. So that's actually what I wrote my thesis on, and that's what I've written most of my papers on. Yeah, so that's the way research works. At least that's my experience. So that's this other option, which is multi-junction cells. So it's actually looking at device architectures. So I spent a lot of time looking at different fabrication, how to make the solar panels. You can also work on the device architectures using conventional deposition and fabrication techniques. So multi-junction cells, just to define them here or to show them, on the left, this is a device architecture of our single junction cell. So this is just a cross-section of a device. This is a cartoon of a cross-section, of course, because we're talking about things that are sub 100 nanometer. So on the left, usually we work on glass Glass is hard and brittle and heavy, but it's easy to work with. So when we were working on device architectures, I worked on glass, even though we did work on paper for other projects. So this is glass substrate, and then on top of it, we have a transparent electrode, interlayer, a subcell. SC stands for subcell, or you can think of it as semiconductor, but that's where the interesting things happen. That's where the light becomes electricity. And then on the top, we have another electrode. And so you have an electrode on either side, and they're going to pull out the charges. But you have one semiconductor in here, one subcell. That's a single junction. That's where you have one subcell, or one diode junction, if you want to think of it again as diode. But here on the right, I'm showing a dual junction where you actually have two of them, and then they're connected here by this RZ. That's basically another electrode, you can think of it. So it's basically two solar panels on top of each other. You can simplify it to that if you're not that familiar with PV or solar technology. But you basically end up with these two subcells, two solar panels on top of each other. And when you combine them, or why would you combine them? So first step, this is another historical paper in the field. If you have done anything with solar technology and device architectures, probably you've read it. If you want to do that, then you should read it. But it has really beautiful pictures. So actually, that's why in my class I tell you that figures are really important. Because here, the picture is beautiful, even though it's older than the average age in this room, I guess. But the goal here, this graph is showing on the bottom, this is the band gap of the semiconductor. On the side, this is the number of photons that you'll actually absorb with that band gap. The maximum power conversion efficiency is shown by this square, actually the integral under the curve, and comes out to 31. So this is the optimized band gap of a semiconductor in a solar panel. And then this is the power that can come out. Because it has to be a rectangle, it can't be the integral under the whole curve here, unless you actually do a multi-junction. So this is a dual junction, and then you can actually, for a dual junction, you have two different band gaps, so you can put two different rectangles in here, and then you're going to get more power out because you're going to absorb more photons with more energy. So you want to get more power out, and so this is a dual junction. Yeah.
Why does it have to be a rectangle?
Because, well, so the band gap of a semiconductor, you can only absorb photons that have more energy than that. All right, so that's what this limit is here. This is your band gap of your semiconductor, and it can only absorb photons with more energy. This curve is actually showing the number of photons with that energy. So if you have this band gap, 1.4 or so, then it can absorb this many photons. So that's actually what this curve is showing. So it's a different, have you seen this chart before?
No, maybe.
Okay. So it's different than the other one. It's nice. I'd love to spend more time on the chart. I'm trying to get to my own research slowly. But this is important background. It's hard to decide what's important background here. But basically, if you have two junctions, then you can have, if you have two different band gaps, then you can absorb different amounts of photons, and you can actually fill in more of the curve and absorb more photons here. So with dual junction, you can actually get up to 50%. So a single junction, the max possible was 37, but if you have a dual junction, the max possible is 50. So this is theory, this is theoretical modeling and pretty pictures, but this has also shown historically, if we go back to our chart of the history of solar technology, and you look just at wafer PVs have been here for a while. The maximum single junction is at 29. That's actually what I pointed out before. But if you do a multi-junction, so this is actually 3 junctions together, you get up to 39. So our best PVs are actually 3 junctions together. So this is the best world record that we have. The ones that are even above it also make use of concentrating, so different optical tricks that will actually increase the number of light that goes in your PV. So this is historical demonstrations with other technologies, other materials. We also modeled what's the best practically possible that you can get out with OPVs. And with OPVs also, you can get a significant increase. It increases the practical limit to 24%. So this is why we look at multi-junctions and have studied the device architecture of multi-junctions to increase our power conversion efficiency in OPVs. So multi-junctions, this is what I wrote the majority of my thesis on, as I said before, and there are multiple aspects in multi-junctions. The interesting thing about OPVs is that they're actually sub 100 nanometers. So they're very thin. So the wavelength of green light actually is around 550 nanometers. Right? I put this on like every single exam in modern physics because I love it. But the wavelength of green light is 550 nanometers. So we're talking about devices that are actually smaller than the wavelength of green light. So that brings in a whole lot of very interesting physics, which unfortunately I'm not going to get into today. But if you're interested, you can read my thesis. But today we're going to talk about number 4. In just a little bit of time I have left, I want to talk about actually circuit theory. For engineers who have seen circuits, we're going to do a little bit of circuit modeling and simulations. This is, again, another aspect of my PhD. All right. So, to delve in, firstly, to start off, I just want to talk about what my materials were. So what the actual devices that I was working with. So we need to have 2 junctions. So this is talking about a dual junction. We use 2 different materials. We're going to look here at this red one, or it's shown in red. This is chloroluminate dicyanine. It absorbs just the red and infrared. Actually, this basically looks transparent to the eye if you make it thin enough. And then DBP, dibenzopyriflanthane, I believe is what it's called, and it absorbs your green to your blue. So they actually have complementary absorption. One absorbs just your red light, and one absorbs your green and your blue light. Which is one of the really interesting things about organics is you can actually find semiconductors that do that. Any kind of your conventional semiconductors, if they absorb red light, then they're also going to absorb green and blue. They'll absorb everything, every photon that's larger than the band gap. So that's one of the very interesting things about organic. So they have complementary, these specific materials have complementary absorption, so they're transparent to each other. They're also quite efficient as single junctions. So as single junctions, that's what we have on the right, this JV curve, the current density voltage characteristic. One is in the red, it's around 3%, and the other is in blue, it's around 4%. So these are actually decent numbers for power conversion efficiencies for single junction OPVs. But our goal is to reach 50% or something like that. So our goal is to make it better, so that's why we're combining the 2. So through a variety of techniques over several years, this is a chart that summarizes all of our work in the different parameters. Here, this A to P, that's our PCE. And we approached 5.5. Actually, we had some that were at 5.9. So we're approaching 6%, which at the time that I did this work, it was one of the highest in the OPV field. But by the time that I published, about a year and a half later, it was behind everyone else. So that's another interesting thing about research. It moves really fast, and if you don't publish immediately, everyone beats you. So that's academia for you. But anyway, so we were approaching 6%. But the interesting thing here that I highlight is the fill factor. So if you remember from the introduction, fill factor has to do with the shape of the curve. Whereas here, this is our JV curve, and so this green is our multi-junction device with the 2 single junctions put together. And this shape is actually pretty rectangular. So this is actually one of the highest fill factors. It still is one of the highest fill factors of a multi-junction OPV. And so after presenting this and publishing it, I'm not going to go through the rest of it, but after doing that, we decided, what we decided is that I wanted to graduate, but my thesis was not long enough. So the question is, what do I do? And I said I didn't want to go back and do more experiments, at least at that point. So I analyzed my data. So I had a whole lot of data. And at that point, including this, I did many different devices here, and this was the best. And the question is, why is it the best? What happened? So I went back and analyzed my data. And so I am in the process of publishing another paper just on analyzing old data. But so if we'll go back and look at fill factor, So here again, we're showing fill factor, and this is the actual numbers here for single junction 1. Actually, fill factor is 0.55. That's this red one. You can see it's not very rectangular. It's more almost like a triangle. It's pretty bad, actually. Single junction 2, 0.73. This is the best fill factor that you get in OPVs. So this specific single junction is actually very, very good, whereas the other single junction is very, very bad. They have different shapes. And the interesting thing is that if they have different shapes, in the single junctions, that causes different shapes in the multi-junctions. So in the multi-junction, you can actually control the fill factor. You can control the different shapes, and it will range somewhere between the fill factor for one and the fill factor for the other. Well, this is our theory, but this is kind of unintentional. We just used these because they had high power conversion efficiencies. But what we find is that because their fill factors are very different, it can give us a very unique study on fill factor itself. What we find actually in a lot of the papers, they say that fill factor, the shape of the multi-junction, the fill factor of the multi-junction depends on subcell current balance. So I didn't spend much time on it in the intro, but each of these subcells are making electricity, right? They're actually generating current from the light. But they generate the current independently. And so we wanted to look at, so that's what I'm calling subcell photocurrent. Photocurrent is the current that's generated from the light in each subcell. And we hypothesized that the high fill factor, the dependence on fill factor is due to the balance of the different subcell photocurrents. So if one subcell is making significantly more photocurrent than the other subcell, it's going to change the fill factor. But this leads to so we say that the multi-junction fill factor depends on the balance of the subcell photocurrents, but this leads to the question of how do you actually quantify the balance of the subcell photocurrents. And so for people in my field, they're familiar with it multiple different ways. There are papers out there that approach it different ways. But we find that none of them quite satisfy, and we actually made our own. So just to go through it, so this is my new term that I made up, SPB. I invented that so I get to make my own name for it. And so that subcell photocurrent balance equals the difference in the photocurrents of the two subcells over the sum of the two photocurrents of the subcells. So this is just how the difference of the subcells over the sum, and so that tells you basically how different they are, how balanced they are. And so you can compare the actual thickness of the subcells of the actual materials, because you might think if you have more molecules, then it will absorb more light and make more electricity. But you can't directly compare one semiconductor to another because it's going to absorb light differently. So you can't do just thicknesses, number of molecules. You can't just directly compare the short circuit current from a single junction. So you can't actually just measure the single junction and compare it to the other single junction, the current coming out, because they're different optical environments. Because the light will reflect differently off of the electrode. I'll leave it at that, although that's, again, very interesting. You can actually model the light. You can actually model the light that's happening within your device, and then you can model how much current you should be able to get out of each device. But we find that our model has non-negligible error. It's error that you can usually ignore, but when we were looking at this balance, we found even a little bit of error overwhelmed and made the trends not correct. So we didn't use that because of the assumptions there. You can actually integrate out the EQE curves, which I haven't discussed here. It's okay, but anyways, it has lots of error. And it's very rare for anyone to make this measurement correctly, which is surprising because it's one of the fundamental measurements. But anyways, so three of these are measurements that you can do. They're indirect measurements that you can do of the subcell photocurrent, but they all have error and they don't directly apply. One of them you can actually model, but our model is not correct. And so we looked in the publications to get inspiration, and one of this is numerical analysis of the JV curves, using circuit modeling here.
So how do you interpret the negative SPB?
A negative SPB. It just means that one of the photocurrents is larger than the other. So Yeah, it just means that one dominates or the other dominates. So it's just a parameter that we pulled out. So if it's positive, that means subcell 1 is making more current. If it's negative, that means subcell 2 is making more current. So it doesn't get plugged into any equations. The sign just tells you which subcell is dominating. Yeah, good question. Yeah, so I'm throwing a lot of letters out here. But yeah, this is a photocurrent from one of them and photocurrent from the other. And it's intentionally symmetrical around 0. I'll show you some graphs in a little bit. So numerical analysis using the circuit simulations, basically. It starts with our circuit modeling of the JV construction. So I have shown here is this extremely oversimplified picture. But if you know anything about circuits, you know about resistors in series, hopefully. So if you have resistors in series, like this, so we have 2 subcells and they're in series. If you put 2 resistors in series, then you know that the current going through each of them must be equal. So the current going through this one must equal the current going through that one. But you know that the voltages add. So the voltages across all of this equals the voltage here and the voltage there. So that's just to give you an idea that currents have to be equal. For anything that's put in series, your currents have to be equal, but the voltages have to add. So that was a simplified picture. But this is an actual JV curve. So this is our current density and our voltage. So we have our single junction 1. So this is actual experimental. We made one single junction. The blue, we made another single junction. And then this dark purple here is our multi-junction that we made. And then in the dashed magenta lines, this is our, what we're calling a reconstruction of the JV curve, where we added 1 plus 2 equals 1 plus 2. So this dashed line is 1 plus 2. And we literally just for every single current, we added up the voltages. And then we made this curve. So it's numerical analysis, but it's basically algebra, really. And then you can see our dashed line falls on top of the solid line. So our solid line is experimental, and the dashed line is what we actually pull out of our numerical analysis. And so from there, we can actually reconstruct the JV curves. But we can actually use as a fitting parameter the short circuit, the photocurrent that's coming out, the short circuit current of each of these single junctions here. So we can see that if you have current matched multi-junctions, so if you have the single junction of 1 equals the current out of one subcell equals the current out of the other subcell, then you get SPB equals 1, right? So this is balanced, where you actually have where we chose for the photocurrent of 1 equal the photocurrent of 2. So this is an example of a device where we have 2 different subcells and it's entirely balanced. It has a power conversion efficiency of 5.7. And the balance comes out to 0. So 0 means that it's balanced. But, yeah.
Is 0 optimal, or is there a reason to want it imbalanced?
No, that's a good question. That's what we're building into. Good question. We'll get there. Yeah, so this is an example of one that's balanced, has efficiency of 5.7. Yeah. So if we actually get imbalanced, so this is an imbalance of 0.09, we actually get a higher power conversion efficiency of 5.9. So this, we figured out what the imbalance is by plugging in with fitting parameters the photocurrents from each of these single junctions. So that's how we can figure out what is the photocurrent of the single junction by fitting it to the curves. And then we can calculate out the SPB, that's an imbalance. We show that these curves are imbalanced and it has a higher PCE. So this is actually better. So the imbalanced device is better than the balanced device. So yes, that kind of answers Drew's question. The interesting thing is, in the field, everyone is convinced that balanced is the best. It has to be balanced. But here, this is actually the first paper where we experimentally prove that balanced is not necessarily best. But this is just comparing 2 devices. You really shouldn't trust anything that's based on just 2 devices, really. So we did this for a variety of devices, and we also did circuit simulation. So before I showed you just 2 resistors in series. The truth is it's much more complicated than that. You have here a diode resistor and a current source in parallel and then another resistor in series. That's one subcell, and this is the other subcell. And we ran a simulation with different, basically different photocurrents that are generated here in this current source. Again, matching it to our experimental data to pull out the fitting parameters of each of these resistance, the diode parameters, etc. And so we have experimental data, we have our simulated circuit simulation data, and this is a plot showing our fill factor. So on the bottom is the subcell photocurrent balance. So this is our calculated out was the balance between the two subcell photocurrents. And so this answers Dr. Cornley's question that 0 is where it's exactly balanced. On the right side is where subcell 2 is limiting. That means it's making less current. Or you can think subcell 1 is dominating with more current. And then on the left, you have subcell 1 limiting. And this is fill factor in blue. The line is our simulation, whereas the triangles is actual experimental data, just for a set of 9 to not make it too crazy on the graph. And then here, this line is actually the fill factor of subcell 2, which was our very high fill factor single junction. On the red line is the fill factor of single junction 1, or subcell 1, which is the very low fill factor. You can see most of the fill factors will fall somewhere in between the two fill factors. So firstly, we see that our simulation is following the experimental data, which is good. And also you see that the fill factor depends on the current limiting cell. So it does depend on the balance of the photocurrents, which was our theory, our hypothesis. Other people have hypothesized it before. This is the first experimental demonstration that fill factor does depend on the subcell balance here for quantifying it. So this is fill factor. It's a little bit crazy graph. I'm going to risk making it even crazier by adding here. On the left is our short circuit current, our JSC. That's the current coming out. On the right is the power conversion efficiency. So our short circuit current is doing something crazy over here, and it's decreasing actually as fill factor increases. But actually we see that the fill factor increase is dominating, and we have a peak in our power conversion efficiency somewhere around 0.05, 0.06. So our best cells, the maximum PCE cells, are going to be around here. So it's actually not current matching. Current matching is another way of saying balanced. Current matching is actually what's much more common term in the field. So current matching is 0, but we find that our efficiency gets better actually if we're slightly imbalanced. So this is with a curve comparing the different subcell photocurrent balances. We can go back to our JVs. They're a little bit simpler to look at. So these are, again, simulated JV curves. And again, it shows in the purple here, this is our current matched or our balanced. And this is our maximum short circuit current. In the field, you see people insist that your devices have to be matched to be any good. If they're not matched, then they're not good. That's just simply not true. You'll also find a lot of people that focus on short circuit current. How can I make this go down deeper? It is very important to get as much current as possible, but at least with our specific materials, we're actually finding the maximum efficiency is out here. Again, we're looking for the biggest rectangle that we can fit in here, P equals IV. The maximum power you can get out is actually out here, so it's not current matched, and it's also not our maximum JSC. So it's, again, contrary to expected. And so we can actually prove through, this is simulation, we can also prove through experiment that actually fill factor is really key as well. People normally will ignore fill factor, but it is quite key. But that's not to say that short circuit current is not important. It just says fill factor is quite important in itself. Another little aspect here that my advisor persuaded me to plot is actually what happens if you're working with different light intensities. So you guys know that the sun is not always at the same light intensity. It changes brightness through the day, right? It gets more, it gets less. The interesting thing also is your solar panel, the amount of current that you're going to get out of your solar panel will depend on the light intensity as well. So that's quantified here as our responsivity. Actually, it comes fundamentally from you get different absorptions of light, or different percentage absorption of light depending on the brightness. If there's too much light, then it's not going to absorb as much as it would if there's a little bit of light. And so that depends on our materials. We won't go into that. But here, this purple line is our subcell photocurrent balance. And we find that that actually changes with different intensity of light. And as our photocurrent balance changes, depending on the brightness, actually our power conversion efficiency also changes. So it depends dramatically if you're working at what we call one sun, which is 100 milliwatts per centimeter squared. That's the actual brightness if you're right under the sun with no clouds. But if the clouds come, then your brightness is going to change and your power conversion efficiency will also change due to the change in fill factor, actually. That's a key aspect of it, among many other things. So this was just a little study to show in real life. So in the lab, we pretend that the sun is always on. There's no such thing as clouds. But this is just a little thought, really, that actually the clouds matter and it's going to change things dramatically. So we need to keep this in mind. So just in conclusion of my research, this again is a whole lot of variables and letters here, alphabet soup. But really we maximized our multi-junctions a variety of ways, but just here we've quantified our subcell photocurrent balance, the balance of the photocurrents via our JV reconstruction and numerical analysis. We find that the multi-junction fill factor depends on the current limiting subcell and how much that subcell is limiting. And we've also demonstrated, this is the first demonstration of multi-junction, which is optimized, or the efficiency is maximized when the subcells are imbalanced. And we actually prove and quantify the imbalance rather than the maximum JSC and rather than current matching. So that's the conclusion of this research. I just wanted to put up one more slide which suggests what my future work is here, because I'd love for Amy and all of you to join in my research. It'll be fun. So just from today's talk, there's circuit simulations. So I want to press forward on the circuit simulations I used for the actual describing. So I fitted it to my experimental single junctions, these two specific materials that I'm working with. But I'd like to explore what would happen if you worked with different single junctions, different materials. Just using circuit simulations. What happens if the resistance increases, for example? So that's a circuit simulation. The very nice thing about that is these circuit simulations are free online, and you can do them on your computer, and we don't have to spend tens of thousands of dollars. And it's very cool, and it's based on, from my empirical data, also looking at PV technologies at non-optimal conditions. As I said, most people are looking at what happens if it's under bright sun with directly shining on it, but what happens if the clouds come, etc., things like that. Which is very understudied. We're also going to work on building the new physics and engineering, and I'm calling it a fab lab, but something about fabrication. So looking at fabrication of PVs, specifically nano PVs with low capital costs. And also, of course, abundant and non-toxic, and investigating the physics of those PVs. So the conventional solar panels that are out there, that's extremely, extremely high capital costs. But the physics of that is well understood. But these very low capital costs PVs that are just not really well understood, so looking at the physics of that, and potentially looking at other nanoscale devices, whatever interest is there. But my focus, my preference is nanoscale. And then continued collaboration with my lab at MIT. There's specifically some experiments I'm finishing up with so-called tri-layer architectures, which I'm not going to get into here because I realize that this video is going to go online, and I'm not going to reveal what I haven't published yet, because people are just waiting to steal your ideas, because I'm sure the whole world is watching this YouTube, right? So anyways, these tri-layer device architectures, working with $1 million equipment that we have at MIT, making multi-junctions with that too. And of course, any other ideas that come along, anyone who wants to propose an idea, I'd love to listen to it and discuss it and see what we can do. So with that, so these are just some ideas of what I have going forward, open to other ideas. And this is just part of my research. I've tried not to show too much of my research here, just for the sake of time and for your interest. I'm sure you're not all PhDs and OPVs. But with that, I thank you for your attention, and I open floor for any questions.
I have a couple of burning questions.
Okay, please.
The first one I think that's probably more significant is, did you develop in doing your research, did you develop any intuition on the relationship between how imbalanced the subcells have to be to get the maximum efficiency? See what I'm saying?
So with these specific materials, that's what we're getting in this plot. We actually modeled out what the imbalance should be for the maximum efficiency.
So that's that point there?
Yeah, so that's this black line is our efficiency, and it maximizes around there. So that's for these specific materials. I'd love to look into other materials as well, if we had more time.
Yeah, the other question is, I was puzzled with your model of the subcell. If you can go back to that circuit.
This guy.
Yeah. So, okay, I can see this current source here, but why do we need that resistor on top? Is that for?
So this, for example, is one subcell. This is a typical. This is actually the conventional model for a photovoltaic. That it has a resistor in parallel and a resistor in series.
Yeah, but what is that model? That's what I don't
So. No, that's a great question. What actually is it? And there's lots of ideas. It depends on your device. It's going to vary a little bit. This, for example, might be the contact between your electrode and your semiconductor, if there's any kind of impurities there. Or there's actually incorporated an interlayer, but if something's going on fabrication-wise, a difference in energies, work functions. Also, sometimes in our laboratory scale equipment, if there's some kind of resistance between your actual probe and the electrode itself. Yeah, good question.
Thank you.
Yeah. Other questions?
Other questions for the speaker?
Yes.
This is totally not your research, because you already said that it wasn't. But so excitons, those are like these little weird pre-electrons that like happen.
What an exciton is?
Exciton, not
Exciton. Yeah. So I love excitons. They're really cool, and they're really misunderstood, very sadly. But so I'm going to tell you my understanding of it. I think most people, well, the fundamental level of what excitons are most people agree on. It has to do with your molecule. So you shine light on the molecule, and you get it energizes the molecule. So an exciton is basically a molecule with extra energy, and so you're forming almost like a dipole on the molecule. But it's not actually free electrons and holes. You can also think of it as electron and hole, which are basically just still stuck on the molecule until they get some energy that actually makes them break apart.
little charges floating.
Yeah, and then they can float around into the wire and charge your phone. Yeah, but they're stuck. They're basically stuck on a molecule. Yeah.
You had a question about the wafer crack.
Yeah.
The one where the top wafer, I can't remember it, but it's the one that you said you showed to your friends and they were like, they don't get it.
Oh, yes, yes. Let me see if I can pull that up. This one.
Yeah, that.
Yeah.
So the best wafer multi-junction, can you do that with more than 3?
Yes, you can. People have tried. You go from 3 to 4. The most I've seen, I think, is like 8 or something like that. But the complication is that you have to have the same current through every solar panel or every single layer that you put together, and it's actually extremely hard to balance that current together. And so fabrication-wise, it's really difficult to get it just right. And so as people go up and up, the efficiency should go higher, but just due to the difficulty of matching it together, the difficulty of actually making it gets worse and worse. So the best we've seen so far is 3. Good question.
So let's go back to one more thing. If you go back to your G versus E curves, we showed those. You're trying to get
Yes.
rectangles as much as possible. It's not intuitive how you get discovered, because it would assume that because you're looking at you want to minimize the resistance, right? So you don't want to make the current smaller, I don't think. Let me show you what I'm saying. If you go to one of those curves where you have those approximate.
Oh, the JV.
Yeah.
Yes. Like this kind?
Yeah, that's something like that. So here you will say the blue is the best. Is that correct?
What do you mean by best?
Because it's the closest to rectangle, so it gives you more power, I think.
Yeah. Well, so your power equals the current times the voltage. The purple one here has a higher voltage. So you do want to draw your rectangle. And so this rectangle would be something like that. So that is very close to rectangle, whereas for the purple one, the rectangle would be something more like that. So this rectangle is actually going to come out bigger. It might not seem like it. The blue one comes out to around 4%, whereas the purple one was around 6 or 5.5. So it's a little bit of an increase. But yeah, so you have to look not just at the shape, but also the voltage, also the current.
Yeah.
Yeah, it's a complicated beast, really.
But I still would think that the voltage is driving it, but it doesn't say it's not that simple. There's some nonlinearities here that are evident, you know? Yeah. Because you just think of it as you minimize resistance, you get higher flow of current, right? So R is V over I, and V is an interval of E dot dl or something, and the bottom is the current density, another interval. So if you minimize that, you increase current, or maximize that, you increase current, because you minimize resistance.
Yeah, so if you minimize that series resistance that we talked about, yeah, it's going to increase your current.
Right.
But you still have that separate current source, is what we're modeling as. That separate current source is the actual molecules absorbing light and generating the electricity. So that has to do with the actual absorption of the molecules and their conversion into free charges. So there is a separate current source, which people work on different materials, different fabrication to optimize that current source. But then there is also work on decreasing that series resistance. So there are multiple different ways to look at it. Yeah, and the voltage is actually controlled partially by the resistance, of course, but also the diode characteristics, which have to do with, so these are photovoltaics, they're diodes between actually 2 semiconductors. I talked about just one, but there's actually 2. And so the choice of the 2 semiconductors and how they match and compare also controls things. Yeah.
I have to grab it.
So you can see why I spent like 2 or 3 years just working on the shape of the curve, not even on the current and the voltage, just the shape. Yeah. Yeah. Other questions?
Should we thank the speaker again?
Thank you.
Start paying these guys to ask questions.
So on the corner, say, ask question, please.
No. You should make it.
Some points, we'll have to decide.
Ex- Exactly. Yeah. Yeah, have to make it extra credit on exams. I think that's what will work, extra credit on exams. Great. Well, thank you guys for coming, staying late on a Friday.